From above him, around him, and below him, man has always been subject to the forces of creation, set in motion by the master planner of the universe. Where do these powers reside, and how are they unleashed? And how do we, the people of the earth, fit into the scheme of things on this thundering earth, with its whirling winds and roaring waters? Regardless of how many times we ask ourselves these questions, we're confronted again and again with the great mystery of creation, finding ourselves filled with renewed wonder at the power and majesty of the awesome forces of God's creation. Hello, I'm Jim Pemble, your guide on this exciting series about the powerful forces of creation at work in the world around us. In the next hour, we're going to witness some of the most awe-inspiring footage ever assembled about the explosive energies that are constantly at work beneath and sometimes above the Earth's surface. We'll learn what scientists have discovered in the past 4 decades about the dynamics of the Earth's interior, how volcanoes, like these in the Cascade Range, are born, and about the conditions that lead to earthquakes and how science is slowly learning to better observe and hopefully someday predict these occurrences with greater accuracy and timeliness. Join me now as we explore the Earth and encounter the great geological forces that shape our lives. Hold on, you're about to experience the full impact of the place we call home, the thundering Earth. We like to think of the Earth as a firm place to plant our feet. Instead, we're standing on a great ball that holds within it energies of unfathomable magnitude. Our planet is more fluid than solid, a great sphere that is in a state of constant change, growing new land masses while consuming others, as a part of a continual process of destruction and renewal. We walk on the Earth's crust, a thin skin of rock that makes up a mere 1% of the total volume of the planet. Just below the crust, a rocky mantle surrounds the Earth's core, a large portion of which is hot, liquid rock. We can't see any of these layers, of course, so how do we know they exist? Well, one way is through seismology, the study of shock waves sent out by an earthquake.
They interact with the Earth just like light waves interact with lenses. And we can use that information to determine the properties of the material that the waves travel through. And this gives us a snapshot of the interior of the Earth.
You know, there are different kinds of earthquakes that you can go through. There's the real shakers, and then there's the ones that kind of roll, where you can have this real queasy feeling in your stomach for a few minutes, and you know that there was an earthquake somewheres, and you just felt like the tail end of it.
One of the gals at the table had been through several minor California-type earthquakes, and she immediately yelled at all of us to jump under the table. There were 3 other people there. So we all got down under the table, which immediately our hands, we were on all fours, were on the ground. And, I mean, literally, the ground was just going like this. And it was amazing to me that the ground didn't just open up, because it was it was cement. So you would think that with that kind of, that much, that it would just open up. And it didn't. And I can remember looking at my hands going like this on the floor, and looking straight outside of a window, I saw one of our company cars that was just going like this. And that was my probably most vivid memory.
When you're asleep and an earthquake strikes, the first thing you think of is that somebody is jumping on your bed. And as you wake up, and if it lasts long enough, you realize that it is an earthquake, especially if you lived in California for any length of time, you know that's what it is. But your first thought is not ever that it's an earthquake.
An earthquake occurs when the boundary between 2 large masses of rock can no longer resist the pressure being put on it, and it slides. Much the same way as if you had a very large block of something heavy laying on a surface, and you were pulling against it and it doesn't budge for a while. And eventually it just lets go and it slides across the surface. That's what happens in an earthquake. And it's such a large area that's sliding, and we're talking miles on a side for a large earthquake, that the whole surrounding rock is set into vibration and starts shaking. And that vibration is what everybody senses as the earthquake. But the source of that was the sliding of the rock along the fault.
The theory of plate tectonics has made us realize that the Earth's surface is divided into about 12 large sections or plates. And each of these plates move relative to one another in different ways. Some plates move side by side, moving past each other. Some plates actually spread apart or move away from each other. And some plates actually move together. And in some cases, some of those plates will be subducted or pushed beneath another one.
The plates more or less store up that energy at the boundaries. The plates, if you were in the middle of a plate, you'll see it's moving all the time, constantly. If you're at the edges of the plate, you'll notice that along the fault, there's no motion occurring. In between, the plate is being slowly bent and is building up energy like a spring. When that energy exceeds a certain point, it slips and lets go, and that's when you have an earthquake.
These tectonic plates get their name from the Greek word tekton, which means builder. When the Earth decides it's time to do some remodeling, the sculpting that can take place is impressive by any standard. Most of us think of California when we hear the word earthquake, and why not? Some of the most severe modern earthquakes in the U.S. have occurred there, including the October 1989 San Francisco Bay Area earthquake and the 1994 Northridge earthquake, further south near Los Angeles. California's reputation as a place subject to frequent earthquakes was firmly established in 1906, when the Richter scale measured an 8.3 tremor, a force strong enough to affect an area of 12,000 square miles, changing forever the city of San Francisco. The Richter scale is the yardstick seismologists use to measure the intensity of earth tremors. It's difficult to appreciate what the numbers on this scale mean until we understand how the Richter scale works.
Is when you go from one unit of magnitude to the next, it's not an addition anymore. To go from 6 to 7 is not an addition of 1, it's a multiplication by 10. And this is in terms of the amplitude of the shaking, how big it is. In terms of energy, it's much bigger. And the magnitude scale was not developed in terms of energy, but we can figure out what the jump in energy is. And each unit of energy is a factor of 30. So when you go from a 6 to a 7, you have to multiply by 30 how much energy was released.
Well, I think in an earthquake, when you've seen how bridges can collapse, the fear is not only driving on them, but driving under them. And I think you tend to just kind of hold your breath until you get out from underneath, just on that outside chance that it's going to come down. And like my worst fear would have been on the Oakland Bridge when that happened, and I did have family that was on that at the time, and it did collapse on them, and they were fortunate to get out.
First thing that happened was the sound. You could hear the rumbling, and then the whole house started to shake, and you couldn't tell whether it was going to get more violent or subside, and it kept getting stronger and stronger and stronger. And they say get into the door jamb. So I ran with the one child to the door jamb and held him, and where I could watch the crib of my other child. And the shaking became so violent that I couldn't stand up. I had to sit down on the floor and the whole house was moving so dramatically that the cupboards were opening up and things were flying out, and our neighbors' chimneys were falling down. And I'll never forget watching the crib with my baby in it just jumping across the floor and hitting against the wall, you know, back and forth and back and forth, and being amazed that she slept through the whole thing. And my thoughts were, this is it, you know, I'm going to die. You know, I really thought, and wondering how to take care of these two babies. And what can I do, you know? But thinking that this was going to be it, the end.
It kind of makes me laugh at our society and in the way that we try to control, you know, the bridges and the buildings, and it's like, well, we can try, but, you know, he's going to have his way.
California may have captured the popular imagination as being the earthquake capital of North America. But that's only because there weren't many people around at the beginning of the 19th century in the central United States to witness the seismic events along a portion of the Mississippi River Basin geologists call the New Madrid Seismic Zone. The New Madrid Seismic Zone is one of the most powerful earthquake zones on the planet, extending through the heartland of America between Arkansas and Illinois. The region was shattered by the strongest series of earthquakes ever known between 1811 and 1812. Quakes registering 8 points and higher began to hit the region with increasing regularity in the early winter of 1811. The earth continued to tremble for months with new quakes and aftershocks.
Aftershocks are essentially readjustments of the fault after the earthquake has occurred. When you get this large, massive slip on a section of the fault, portions of the fault are kind of left behind, you might say. And when they're left behind like this, there's a lot of stress in those small areas that are left behind, and that stress needs to be released. And so after the major earthquake, there's all this settling and adjustment, particularly at the edges of where the earthquake occurred. So these will occur over time, and the adjustments, of course, that are needed become less with time, and therefore the aftershocks decay with time. But the definition of aftershock is pretty subtle. It's kind of hard to say what comes after an earthquake.
At the surface, anyone observing the Mississippi River would have found it very easy to relate what happened after the series of 1811 New Madrid earthquakes. Although difficult to imagine, when looking at the great wide flow of the Mississippi today, the earthquake of the early 1800s caused whitewater rapids to form in the river, as the river's floor was thrust upward. Portions of the river even flowed backwards as the shock waves propelled the water upstream. An area the size of the state of Tennessee was scarred by the most severe effects of the quake. People throughout the East Coast felt shock waves. Severe shaking was reported in St. Louis, Missouri, 125 miles from the quake's epicenter. 300 miles away in Cincinnati, Ohio, people also reported feeling the earth move. The enormous seismic waves generated by the quake were passed through the Appalachian Mountains and hit with measurable force all along the Atlantic coast. Some of the residents of Washington, D.C., hearing their furniture move about in the night, thought they were being robbed. From Florida to Canada, New Madrid announced its presence. 2 million square miles were affected by those quakes nearly 200 years ago, more than half the continental United States. The largest area on Earth we know of ever to be so dramatically affected by earthquakes. The New Madrid quakes, however, were not the largest quakes on record. There are instances of modern quakes whose enormities are almost impossible to grasp.
Well, certainly one of the ones that seismologists consider infamous is the one in South America, along the west coast of South America. The reason seismologists are so interested in that one is it's the source of the largest earthquake we've ever recorded, and that was in 1960 in Chile. And that earthquake measured a 9.5, and it basically ruptured the fault the entire length of northern and central Chile. and such an enormous earthquake boggles the mind. It's 600 miles long, and it's hard to conceive of. It took several minutes just for the break in the fault to get from one end of the fault to the other.
The monster quake of 1960 in Chile unleashed energy equal to 1/4 of the world's nuclear arsenal. Another example of such monster quakes took place at 5:36 p.m. on March 27, 1964, in southern Alaska. 12 miles beneath the coast of Prince William Sound, the strongest North American earthquake on record, 9.2, occurred when 75,000 square miles of ocean rock tore against an equal amount of the continental crust. As the energy from this encounter raced through the Earth's crust, places as far away as Chicago and Boston were raised 2 inches. Water levels in South African wells were lowered. In Alaska, ground that was solid turned gelatinous. Massive landslides resulted as millions of tons of surface soil and rock no longer had anything to steady themselves on. Enormous yawning crevasses opened in the ground. Giant waves, tsunamis, were triggered that sent walls of black water crashing on shorelines throughout the region. Far from being simply a concern to Californians, earthquakes are possible anywhere that the Earth's tectonic plates are at constant war with one another. 90% of all earthquakes happen along plate boundaries. When they happen, their seismic shocks travel enormous distances through the solid, dense materials that make up the plates. Along the famous San Andreas Fault in California, the effects are readily evident and form a constant reminder of the possibility of recurring earthquakes. Sometimes, as in the case of the New Madrid seismic zone, the evidence lies hidden far below the surface. The zone is buried beneath 3,000 feet of mud. Today's earthquakes, represented by these cubes, occur along faults in the zone 2 to 10 miles below the surface. The origins of these modern quakes can be traced to the early geological history of North America, when the continent was being gradually torn apart, making way for magma that moved towards the surface, forming volcanoes. If this common geological process had completed itself, North America might have been forever split in two, and today sit at the bottom of the ocean. As things turned out, the volcanoes in this rift became extinct, and the crust cooled and collapsed, forming a wide valley. For a time, an ocean did cover much of North America. Gradually, sediment collected in the rift left behind by the seismic activity, and after the oceans receded, the Earth made another attempt at pushing magma to the surface. But the activity finally stopped, and once again the crust sank. More sediment was deposited by erosion, and the Mississippi River began flowing over the shattered, rifted rocks below. The stage was set for the great quakes of the early 1800s. If most earthquakes are caused by the movement of the Earth's tectonic plates, there are some seismic events, also often associated with earthquake activity, that offer us some of the most dramatic displays of God's power, the volcanoes of the world. These two are most frequently found where one plate meets another.
Even being as frightened as we were as children, there was nothing more fascinating than going up to see the actual creation of Earth, new land. And so every eruption, major one, I was there with my family, right there at the edge of the observatory, and loved it. There was no fear in that, as long as we knew we could escape should the volcano start to flow. And so I was mesmerized. There's nothing like looking over the edge and seeing the Earth be created.
Volcanoes tend to be located in long linear chains that we can find in very obvious places, like the Cascade Range, also like the volcanoes that form along the Aleutian Island chain. most of us, when we think volcanoes, think of volcanoes that are located on land, things that we can see and that have big structures and are very obvious to us. But most of the Earth's volcanoes are located underwater, where pieces of the Earth's crust are being pulled apart. And it's along that seam where lots of molten rock is rising to the surface and erupting as primarily lava flows. And the eruption of those lava flows then help form new crust where these two plates are being pulled apart. Well, as new crust is being formed on the Earth's surface, because the Earth itself does not get any larger year after year after year, parts of the Earth's crust has to be taken away somewhere else on the planet. And it's taken away in areas where parts of the Earth's surface is being subducted beneath another. And it's that process of subduction that also leads to volcanism at the Earth's surface. The reason that volcanism occurs at the Earth's surface is that in the process of that subduction, molten rock is being melted above the subducting slab. And molten rock, since it's more buoyant or lighter than the surrounding rock, tends to rise upward until it either reaches a place where it can't rise anymore and then solidifies below ground, or makes its journey all the way up to the surface to erupt as volcanoes.
A few volcanoes are associated with the spreading center, or the mid-Atlantic ridge. Most of them, though, are related to the subduction zone. On the globe, most of the volcanoes are in fact around the Pacific Ocean, which is the disposal system, if you will, in the plate tectonic system. The plates are under thrusting, going under North America and on around to eastern Asia and New Zealand, Japan, I mean all these around the Pacific Ocean Ring of Fire.
The Vents group is interested in seafloor processes that are occurring at the Juan de Fuca Ridge, which is an area of active seafloor spreading that lies about 300 miles off the coast of Oregon and Washington. And the Juan de Fuca Ridge is an area where the seafloor is actually splitting apart, and it's causing two plates to separate from each other. There's the Pacific plate that's heading out west towards Japan and the West Pacific, and then there's the Juan de Fuca plate that's heading towards the continent, towards North America. And when it reaches the Oregon and Washington coast, it dives underneath the continent and gets what we call subducted into the Earth.
On the Earth's surface, there are several types of volcanoes, depending upon the composition of the materials they're made of and the particular geological forces that created them. Cinder cones consist of loose rock fragments called pyroclastics, ejected from a central vent. Shield volcanoes, like those in Hawaii, are broad, gently sloping cones made of solidified lava flows. A composite volcano is made of alternating layers of pyroclastics and rock solidified from many lava flows. A variation on these themes includes calderas, depressions much larger than the original crater, like the beautiful Crater Lake in southern Oregon. Here, the crater floor collapsed into a vacated magma chamber beneath the volcano, eventually filling with water. Perhaps the most infamous example of a caldera is that inside the crater of Mount St. Helens in southwestern Washington state, formed when exploding gases blew away the mountain's summit on May 18, 1980.
On my way back to my hometown of Spokane, Washington, we were driving in the car, me and my friend, and it just turned pitch black. There was nothing. You couldn't see anything. It was just all of a sudden just blackness. And I actually thought at that time that it was God's time. I really did. It was just incredible. In the middle of the day, you know, it was supposed to be light out, it turns pitch black. And then we were driving along and we noticed that it was like smoke, except it wasn't smoke. The car died on us because of all the ash from the volcano that blew up Mount St. Helens. And we didn't know it was a volcano at the time. We didn't know what it was. So our car had died on us. We stopped on the side of the road. Well, luckily the battery was still going. And we turned on the radio, and that's when we found out that Mount St. Helens had blew up.
Until that day in 1980, most of the people of the Pacific Northwest thought of the Cascade Range of mountains, of which Mount St. Helens is a part, as scenic backdrops to their daily lives and as places to ski, hike, and climb. Geologists who specialize in volcanism, the study of volcanoes, knew otherwise. They knew it was only a matter of time before one or another of the Cascade Peaks erupted. Mount St. Helens, which had last erupted in 1857, began to announce her intentions in March 1980. In less than 3 months, its summit was transformed from a serene snow-covered cone to a gouged-out remnant of its former self.
There are many different ways that we can tell when a volcano is becoming more active. One of the most obvious one, of course, is when a volcano that was previously quiet all of a sudden starts steaming, that there are new vents forming on the crater floor or in the summit crater of a volcano that releases water vapor. So obviously when that situation arises, something is causing that volcano to become active. Is new magma being injected into the interior of the volcano so that it's heating it up? Or maybe there's a change in the hydrothermal system within the volcano.
Ash and steam eruptions began on March 27th and escalated over the following 6 weeks. Superheated steam began to rise from water that had seeped into the mountain, coming into contact with its volatile interior. Thousands of small earthquakes began early that spring, bringing seismologists and other scientists, as well as curiosity seekers, converging on the mountain.
The most important precursor for volcanic eruptions are earthquakes. And these are earthquakes not related to the movement of the Earth's plates or crust, but related to rocks breaking due to the upward rise of molten rock toward the surface. As that molten rock rises toward the surface, it has to make room for itself. It forces its way through the existing rock, it breaks them, pushes them aside, and each time it breaks, those rocks break, it leads to an earthquake. At Mount St. Helens, before the big 1980 event, there were two key factors that were really important, as it turns out, to the eruption, the big eruption. The first was earthquakes. There were over 10,000 earthquakes that occurred between March and May 18th of 1980. Perhaps more important for what actually happened on May 18th is that the whole north side of the volcano was being pushed outwards to the north about 5 to 7 feet per day. And during a 2-month period, the north flank of the volcano actually was pushed outwards about 300 to 400 feet from what it was the previous year. This was telling the scientists at the time that magma was rising into the volcano and pushing the north flank outwards, and therefore creating a very unstable situation on the north side. The volcano was literally being wedged apart by that magma rising into the cone. As it turns out, a very large earthquake triggered the May 18th eruption, a magnitude 5.1 earthquake. It shook the volcano, and that north side, that unstable north side, slipped downward as a huge landslide, which in turn triggered the huge explosive eruption out the north side.
When the eruption occurred that sunny Sunday morning in May, it destroyed the summit and the north flank of the mountain almost immediately. All wildlife, vegetation, and topsoil was stripped from an area extending about 6 miles outward from the explosion within seconds. Miles of forest were instantly leveled as an enormous mass of super hot gases and volcanic rock fragments roared down the side of the mountain, sweeping away more forests. Everything within 15 miles of the north face of the mountain was flattened or buried by 670-mile-per-hour scorching ash clouds. For 30 hours, exploding gases continued to froth magma and ash vertically into the atmosphere. Airplanes had to be diverted around the cloud. Ash continued to fall for days, as far away as Montana, making many places look like midnight at midday. Much of the north face of the mountain slid into picturesque Spirit Lake, filling it with debris. As a result, the lake is now much larger and shallower. Mount St. Helens was a volcanic wake-up call. For in addition to the obvious problems caused by such eruptions at ground level, potentially disastrous results can occur also high in the atmosphere.
These images we're looking at are from the geostationary weather satellite operated about 35,000 kilometers or 26,000 miles in orbit above the Earth. This is a volcano from 1993. The volcano's name is Lascar. It was in Chile. This is Chile, this is Argentina, this is Paraguay, this is Brazil. And what we have is a series of eruptions that are occurring over about a 10-hour period. And the ash plume is moving off to the east, and there are several discrete events. We need to be able to track volcanic ash so we can warn pilots, whether they're commercial airlines, whether they're small aircraft pilots, whether they're military operations, that this is a hazard, and if there's volcanic ash, they have to avoid it. And the only way to avoid it is to know where the ash is.
We have geostationary satellites which are launched into an orbit 22,000 miles above the Earth that move at the same speed the Earth rotates. Therefore, the satellites are in a fixed position in respect to the Earth. And then we have polar orbiting satellites which circle the globe constantly to get global data.
Since the eruption of Mount St. Helens, scientists have been using the mountain as an outdoor laboratory, gathering data that may someday make it easier to predict such events. Several volcanic eruptions and earthquakes have occurred around the world since Mount St. Helens erupted, and scientists have used every opportunity to enhance their knowledge and their skills. Still, the chances of developing accurate methods of predicting earthquake and volcanic activity remain elusive at best.
We can predict where earthquakes are going to occur generally because they occur around the Pacific Ocean and some other well-known features. So that part is fairly straightforward. The question is when and where and how big. And if you can get all three of those, that's what you need for a prediction. And if you can't get all three of those and you're just throwing out a bunch of potential places, you really haven't done the job of predicting them. You just, you can take a map of earthquakes around the world and then say next year that's where the earthquakes are going to be. In that sense, yes, you can predict them.
Prediction is probably the one area in seismology that's been the most stubborn to research. And I think we're making progress. I think that one area we're making progress in is long-term predictions, determining how likely one area of the world is to have an earthquake as opposed to another. And this helps for general planning. How strict do earthquake codes need to be in that area when you're building your buildings and things like that. However, specific predictions and short-term predictions have not yielded to seismic research so far. There have been some very interesting cases where individual earthquakes have been predicted based on very specific observations, but it's turned out that those observations don't help us on other earthquakes. And finding a common factor has been, so far, just has not been productive.
We currently are not able to forecast a volcanic eruption at a particular volcano a few years or a few tens of years, hundreds of years, or thousands of years ahead of time. There is a strategy, though, that we try to use to get at just that question. And that is, we try to quantify or try to determine what a volcano's past behavior has been in terms of the styles of eruptions and also how frequently the volcano has been active. And sometimes we can detect a style of eruption that's very common in a volcano's history based on the rock deposits that have been formed in the past. And sometimes those eruptions do occur on some kind of a cycle or on a time period that seems pretty similar.
I think that growing up with the volcano so very close by, I feel that there's a deeper appreciation as children and then as adults of what Earth and Earth's forces, natural forces, can do.
Volcanoes announce their intended arrivals, as Mount St. Helens demonstrated, with varying forms of seismic activity, which scientists can measure. Earthquakes, steam eruptions, visible bulges of earth, and so forth. Before a big quake, small cracks may open within the rock formations near a fault line. The magnetism, electrical resistivity of the rock, or the speed of seismic waves can change within rocks, all lending themselves to observation. Some methods of prediction involve garden variety common sense. Water levels in wells often rise or fall prior to a quake. The surface of the earth may tilt or elevate, changes that can be readily noted. Chinese scientists, and anyone in Southern California with a pet, claim that dramatic changes in animal behavior are successful earthquake predictors. Horses, dogs, and cats are known to become skittish, and snakes leave their underground holes in droves just prior to the movement of the earth. Following the geological history of fault lines is another method being worked with today. The patterns of past quakes in time and space led geologists in the U.S. in 1988, for example, to predict a 50% chance of a magnitude 7 quake near Santa Cruz along the San Andreas Fault. In 1989, a 7.1 quake occurred on that very section of the line. What will future earthquakes be like? We're still a long way from being able to make such predictions with any great accuracy. One Old Testament prophet, Zechariah, writes of a future quake so powerful that it will split the Mount of Olives in the Middle East in two, creating a deep valley between the two halves. Still, it would appear, at least for now and into the foreseeable future, that as with the weather, there will always remain those elements of unpredictability, which come under the heading of the chaos theory. In other words, there are simply too many variables for there ever to be a chance of total earthquake predictability. Tiny differences in input can rapidly become overwhelming differences in output.
I think more what chaos tells us is that unless we know the initial conditions well enough, which we generally don't, because we'd have to know them to quite remarkable precision, that our predictions will vary from what in fact occurs. There are many factors that can affect the interaction of the two plates along the fault. And when you consider all these factors together, a slight change in one of them at one point in time can greatly change when you would expect the next earthquake to occur.
The fact that we're not likely to ever completely plumb the depths of creation's mysteries can bring us to a deepening sense of the gift of life we've been given on this tiny globe called Earth. Despite their day-to-day immersion in the hard data of their craft, the scientists who study these phenomena aren't immune from a sense of wonder either. Many of those we spoke with had a story to tell which reflected the depth of their respect for the awesome forces of God's creation.
It's always fascinated me from when I was young. I've always been fascinated by the power of earthquakes, the power of volcanoes, the the other power that I see in the earth. And I still am. For example, I love to go out and watch a thunderstorm. It's just that fascinating. And seismic activity, earthquakes, is one of the things that caught my attention early on. They seemed so different from your everyday experience and so powerful that I just felt I had to learn more about them.
Grew up in Texas, and we had hurricanes, and I respect the hurricane as a potential damage, but I was never awed until Mount Pinatubo in the Philippines, and we were watching it here. We'd seen a number of volcanoes, but nothing of this magnitude. I mean, this was 1,000 times worse than St. Helens as far as I'm concerned. Maybe not in a geological aspect, but from a satellite analysis perspective, this was an extraordinary event. And then to understand the consequences of it, not only on the immediate people living in the Philippines and the airlines that were flying throughout the Asia theater, but also what happened in the climate over the following 2 years, where the Earth's climate was affected. Temperatures, if you looked at all the temperatures around the world, it's estimated the global temperature cooled about 0.5 degree Celsius, 1 degree Fahrenheit, from one eruption. If we were to have many of these scale things going on, I mean, that awed me.
I think my most exciting class that I attended in college was when my geology instructor started talking about volcanoes. And I always thought of volcanoes being somewhere else, often Hawaii, where they erupt all the time. And certainly not here close to home in the Cascades. And when Mount St. Helens erupted, it was really awesome to comprehend, to think about volcanoes being active here close to home. And working on volcanoes is really exciting. It's sometimes dangerous, and I love it.
I think a lot of scientists who are not Christians or who don't have a concept of God or of a creator, they're very interested in how things work, because that's what all of the scientists are really after. We want to, in the case of geology and geography, we want to know how the Earth works and what are the different processes that go on, and how does one thing tie into another. But in terms of the situation that I'm in, affirming that there is a God and a creator, I also have a little bit of an idea of the why, like why we have the Earth the way it is, and why it's such a beautiful and intricate and terrific place. Because we have the creator is a loving creator and a very creative creator. I mean, the kinds of things that we've seen on the seafloor, it's like, oh my gosh. I mean, that is a really neat creature, and God must have really been in a interesting mood when he created that thing. And I think he loves us, and he wants us to enjoy creation and be inspired by it. I'm inspired by what I do and about the discoveries that we're making. And that inspiration makes me a happy, it's part of making me a happy person and a fulfilled person.
The Earth is but a speck, circling an average-sized star we call the Sun, one of billions of stars within the Milky Way galaxy. An average-sized swirl of stars, one amongst billions within the enormity of the universe. But we have been blessed with a uniqueness that separates us from every other planetary body in the heavens. How could this have happened? Although he didn't have the scientific understanding we enjoy today, the author of Psalm 104 understood the significance of Earth's uniqueness. Nearly 3,000 years have passed since he expressed, in the exquisite poetry of the Old Testament, his grasp of the fact of creation. God, he said, wraps himself in light as with a garment. He stretches out the heavens like a tent and lays the beams of his upper chambers on their waters. He makes the clouds his chariot and rides on the wings of the wind. He makes winds his messengers, flames of fire his servants. With every breath we breathe, we have another momentary opportunity to witness the gift of life, to look around us and see the awesome forces of God's creation at work.